Hi, everyone. My name is Ke. I'm the executive co-director of the Pittsburgh Quantum Institute. Welcome to this week's PQI seminar. Our speaker today is Dr. Arthur Davidson. Dr. Davidson is a retired professor from EC department at Carnegie Mellon University. He got his PhD in applied physics from Harvard University and had worked in both industry and academic, and we recently know in very diverse range of fields throughout his career. And he joined CMU in 2003 and served as the executive director for the SRC Center for Circuits and System Solutions. And I think today he's going to talk about rings and tunnel junctions and quantum mechanics on any circle. Welcome, Arthur.
Okay, thank you. So let me see. I do share screen, and then I pick my slides. So I see my slides. Everyone, this is the first slide, rings and tunnel junctions, quantum mechanics on any circle.
Perfect.
So my first job after I left Harvard in 1976 was at IBM working on their Josephson computer project. So Josephson junctions are not new to me, although quantum Josephson junctions are. What we did in the 1970s was all classical. Of course, it didn't work. Okay, so there's a couple of comments here on the first slide. Continuity on a twice connected coordinate precludes gauge invariant wavelengths. And for some reason, I'm the first person that I can find that makes this statement after 80 years of quantum mechanics. There are non-superposable eigenstates. Most people learn that all eigenstates are superposable, but in this problem, because of the gauge invariance situation, there are solutions which cannot be superposed. There are eigenstates. That is, an individual solution are good, but they can't be superposed. So how do I get to the next slide?
It might just be clicking, or if you're on a computer, just the space bar.
There we go. All right. So what I'm working on goes back to 1983, mostly at IBM. This top paper here is 3 people at IBM, Marcus Bodeker, Josef Imre, and Rolf Landauer, 3 famous people who worked at IBM at that time, and I was there myself doing some other stuff. And Bodeker, Imre, and especially Landauer sort of poetically derived the quantum mechanics of a particle on a circle. And they said that just as a hypothesis that it's a Bloch wave. Just like in solid state physics where you have a lattice, to get the electron through the lattice, you need a Bloch wave, not a standard wave. So they hypothesized that a circle would also have Bloch waves, although they didn't really prove it. And I don't think they ever pointed out that the Bloch wave would be discontinuous on a circle. And I have a little note here in this red box that this applies in real space and in electromagnetic space. And then I have 3 more papers by a combination of Likarev, Zorin, and Averin. They're Russians, although they're all in the States since the middle 80s when we were publishing these things. And they take the opposite point of view. I crossed it out here. It says quantum Bloch waves cannot exist on a circle in electromagnetic space. So there's a dichotomy. And people don't realize there's a dichotomy because both groups of people use Bloch waves. It's just that Bodeker, Imre, and Landauer say everything is Bloch waves, including circles. Whereas Likarev, Zorin, and Averin say lattices have Bloch waves, but circles don't. And they make a very important distinction in that way. And nobody in this group of papers, and in fact, I don't think anybody going back to the 1930s, tried to worry about gauge invariance of a particle on a ring. So I want to establish a little bit about entanglement and superposition, because I'm going to get back to it. And in quantum mechanics, especially quantum computing, entanglement is the whole thing. So let me see if I can move my picture a little bit so I can read this. Quantum entanglement occurs when a group of particles interact such that the quantum state of each particle cannot be described independently of the state of the other. So everything is mixed up together in a nonlinear way when you have entangled qubits, entangled quantum bits. And then I'm going to distinguish that from superposition. And I guess what I'm saying is I've proved the usual statement of superposition to be wrong. That is, you know, in the hydrogen atom, which is three-dimensional, this statement is okay, that any two quantum states can be added together and the results will be another valid quantum state. And conversely, every quantum state can be represented as the sum of two other distinct states. And since the Schrodinger equation is linear, any linear combination of solutions will also be a solution. So what I've found in analyzing gauge invariance of a particle on a ring, which is one model of a Josephson junction I have here on the left. What we show in this work is that some eigenstates of a Josephson junction are not superposable, even though they are valid eigenstates. And so this definition of superposition is good for three-dimensional things like hydrogen atoms, but not two-dimensional things with holes, like Josephson junctions. And so I'm going to describe this and the implications, which are, well, you'll see you have to change your expectations. Okay, so in 2018, I published this paper, Nanocircuits and Loop Structures, Continuous Waves Preclude Gauge Invariant Wavelengths in AIP Advances, which is an open journal that anybody can download this paper. And I give a link to that paper so you can do it. And then I have three sort of conclusions based on how this paper works. So a doubly connected circle can consistently model behavior for normal and superconducting devices. A doubly connected circle, just any circle, is doubly connected. And what that means is if you want to disconnect a circle, you have to make two cuts. If you just have a straight line or a three-dimensional space, those things are simply connected. You can make one cut through free space or one cut on a straight line, and you have two parts. But if you have a circle, you need two cuts. So, you know, this is qualitatively and quantitatively different when you have a circle. And gauge invariance on a circle implies that any single momentum eigenstate can have any real momentum. And again, the standard solution, if you look on Wikipedia, or almost any textbook, is that the quantum particle on a circle is quantized. And what I'm saying is the momentum is not quantized, it can have any value. And then number three, nonlinear boundary conditions allow a subset of momentum states to be superposable. Now, I've looked a bit at the Google paper from last November, where they talk about some of these things. And I think mostly that I can't complain about what they do, but they miss some details. And there may be some things that could be connected if they understood what I'm saying, and if what I'm saying is right. Okay, so the first issue is gauge invariance. And a lot of people have never studied gauge invariance. So I want to give a simple example here where I have a one-dimensional problem with a coordinate S. And I start here with a Lagrangian, L1D. And there's a kinetic energy, ms dot squared over 2. There's a potential energy V, which is conservative. And there's another potential energy term, which looks a little bit like an electromagnetic term, the velocity of the particle with the vector potential. And then the total derivative of an arbitrary function. And the thing with Lagrangians is you can add the total derivative of an arbitrary function to a Lagrangian, and it doesn't change the answer. And that's gauge invariance. So the choice of that function is your choice of gauge. And basically anything that sort of obeys the basic boundary conditions of the system could go in there as a function. So, and you could multiply it by any constant, and it won't change the result. And so if you want to calculate the momentum, we know that that's the partial of the Lagrangian with respect to velocity, dl ds dot. And you can see I've got it there. It's equal to ms dot plus E0a plus d by ds dot of the derivative of this gauge function. You can go through the math, and the derivative with respect to s dot of the time derivative of the gauge function is logically equivalent to the partial derivative of the gauge function with respect to the coordinate, which is this term here. So when you add this term to the Lagrangian, we add the gradient of the gauge function to the momentum. And since I'm doing everything in one dimension here, to leave it simple, there are no gradients, just derivatives. And then we have the Euler-Lagrange equation of motion, which is the time derivative of P, the LDS dot, is equal to the LDS, which is Newton's equation. So it says that PC dot is equal to the force. And I've put in red these two terms. This one term, d by dt of dE ds, is the time derivative of this term. And here we have the spatial derivative of dE by dt. And for non-problematic functions, these two terms are equal. That is, it doesn't matter which order you take the derivative. I know there are some functions where that's a problem, but most functions in physics, it isn't. And so the thing is that this gauge invariance is exact, that these two red terms cancel. There are two of them, and one, they're on either side of the equal sign, and they cancel. And so the final equation shows the equation of motion for PC dot is ms double dot plus E0a dot is equal to minus dVds, Newton's law. And the gauge terms drop out. And they drop out not because they aren't arbitrary, they drop out because of the way it's put into the Lagrangian. So you can add this arbitrary term to the Lagrangian, and it doesn't make any difference to the equation of motion. And there are certain things which don't make any difference, but which still appear in the equation. In this case, it's a hard subtraction. The gauge invariance, the type of gauge invariance that I'm talking about, makes two terms which cancel. Exactly. So they disappear completely. Okay. For a tunnel junction, which is basically a capacitor where the insulator is so thin that electrons can tunnel through it. And there are two models. One, in my model, which I published in 2018, is a ring in electrical space. And the other model is the one from 1985 and 1986 by Lagrange, Zorin, and Averin that I mentioned before. So on the left, over here on my side, I have Bloch waves, and the Bloch waves are discontinuous. And so that, that's a potential problem of my model. On the other hand, everything is defined. I can talk about the ring above and below a superconducting transition. So above the superconducting transition, it's a normal capacitor that tunnels. And below the superconducting transition becomes a Josephson junction, which tunnels. And if you look at the other point of view, which is Lagrange, Zorin, and Averin, they decided that a discontinuous Bloch wave was unacceptable, and therefore you couldn't have a circle. And so their system, the coordinate for the quantum system is just a straight line off to infinity. And the problem with that is down here, above TC, above the superconducting transition, there's no periodicity. It's just a straight line going to infinity with no particular potential. And so there's no quantized behavior. If you have an isolated electrical capacitor, we expect to have quantized charge on it. That's what people measure. Whereas the solution of Zoran, Likharov, and Averin is that there's no quantized behavior above TC. So that's a problem. So both sides have a problem. They both have a flux quantum h over 2e below TC where there's a superconductor. And it's h over 2e because of Cooper pairs in both cases. Okay. Any question about these two models? We'll get in more. If you thought of a question, you can probably ask it later. Okay, so let's sort of get right to a 3D electromagnetic field and write a classical Lagrangian for it. And the reason I do that is it's very simple to go from a classical Lagrangian to a quantum Hamiltonian. Right? There's no ambiguity. And for the electromagnetic system, which has these total time derivative of an arbitrary function, in this case it's chi, there's a very simple, it's a very straightforward, it's a recipe to go from a Lagrangian to a classical Hamiltonian and a quantum Hamiltonian. So the point is we take a 3D region of space, which in topology we say is simply connected. That means if you start at any point in this 3D region of space, you can get to any other point just by moving the point where you are. There's nothing to stop you. There's no hole anywhere. Okay, so the particle position is also defined that all vector positions are. So here's an R. That's just all these positions inside the sphere are. I took one such position and pointed it out, and I could write the equation of motion for a charge there, which is based on this Lagrangian, which is the difference between the kinetic energy and the potential energy, including this external term, and the time derivative of an arbitrary function. And I changed the name of the arbitrary function because in electromagnetism, the arbitrary function is different from the arbitrary function in a ring. Okay, so let's see, let me go back. This function here is the velocity of the particle vector dotted into the vector potential. So there's two vectors, the velocity and the vector potential. There's a dot product here. And the velocity, of course, is the full time derivative of the position of the particle. And so this is a standard way of writing this. So it's basically r dot dotted into the vector potential. I want to point out, because it's going to be useful later, that that's not the only way you can do it. In fact, there's you can choose any gauge you want. You can change that in arbitrary ways. And the obvious way to change it is to say that we could start with, instead of the velocity dotted into the vector potential, you could start with the position dotted into the time derivative of the vector potential. So I have two Lagrangians here. On the left, I have the standard, let's see, I guess on the right is the standard formulation. Velocity, these are one-dimensional things, so I neglected to put the dot in between the S dot and the A. So the Lagrangian has this force term, it's an energy term, on this side, which is what you'll find in textbooks, which is the velocity dotted or multiplied by the vector potential. And over here, I have minus E0, the position dotted into the time derivative of the vector potential. And so by the principles of gauge invariance, we should get the same answer regardless of which way we start. And so you can take you can find the momentum each way. So very often you get the canonical momentum is the regular momentum, ms dot, plus a term dependent on A. But in the other case, we get the regular momentum minus S times the gradient of A. And then we take it a step further, and we take the time derivative of the classical momentum, on one side and on the other. And the math is more complicated on the left, but it works out that on the left we get ms dot is equal to minus E0 dA dt. And on the right, we get exactly the same thing, although it's easier on the right. Because it's easier on the right, that's what textbooks do. And they don't bother to tell you it's arbitrary. And, well, so, you know, I want you to learn to keep an open mind about gauge invariance. And the difference between the left and the right is a different choice of gauge. All right. So, now we're going to solve the problem of a particle on a circle in an electromagnetic field. And I'm going to say it's the exact same problem as the current through a tunnel junction or a Josephson junction. So while keeping the 3D field, restrict the particle to a circle. Fields are defined throughout the 3D volume of each vector position R, like this. The particle position S is restricted to a ring, which has a hole in it. And since the direction is always along the 1D circle, S is effectively a scalar. The relevant component of force on the particle for the external field will be directed along the circular path. Since the generalized forces on the particle are always along the 1D ring, they are effectively scalar quantities. And so I wrote again the Lagrangian with a vector potential and this chi gauge function for a particle, general particle anywhere in the 3D sphere. And then the Lagrangian for a particle only on the ring. And when you're on the ring, you need two gauge functions. You still have the 3D electromagnetic field, where chi does not change and does not change the actual fields. The chi gauge function drops out of everything when you get the equation of motion. But there's another gauge term as well, which is the Greek letter xi, which is only a function of s and t. It's not generally a function of r. And it's also a total time derivative. And an arbitrary function in that position, and a function of s and t, also does not affect the ultimate solution of the equation of motion, the Euler-Lagrange equations of motion of this L1d. Okay, so I'm pointing out that in this circumstance where we have two symmetries, we have the symmetry of the electromagnetic field and we have the symmetry of this particle in a circle, and they're different, we can account for that, sort of, with two different gauge functions. Now, the truth is that both of these gauge functions can be zero. We can ignore them. But then we lose this insight that there are two symmetries involved. Okay. This was difficult for me to figure out, but this appears to be true. So I'll read it. Neither gauge function of the particle nor the gauge function of the 3D electromagnetic field can affect the electric or magnetic fields for different reasons. And there are papers in the literature where people, physicists, famous physicists, sort of go through, they realize that they're using a gauge function which is not defined everywhere, but they don't point it out. And they reach the same conclusion I do here, but they don't realize that you could use two gauge functions. So what I'm saying is, in this situation, you need the chi gauge function for the 3D field. And it's just what it was before. And it's continuous and it's defined everywhere, so it can have no circulation, no effect on the magnetic field. But we can also have this xi wave function of s and t. And the 1D circular path has no associated simply connected surface. If you don't have a surface, you can't do Stokes' theorem. If you can't do Stokes' theorem, you can't affect the magnetic field. And so when you have a ring with a hole in it, sort of a 2D ring, that's another configuration where the gauge function, for different reasons, can't affect the magnetic field. So we need two things to account for this. We can sort of keep chi inside the vector potential because we don't really use it much. It's useful sometimes to point it out. But we need xi, because xi tells us how the particle on the rings is allowed to behave. Okay, so let's compare Lagrangians. So on the left side here, I'm talking about charge on a ring, and the ring has a coordinate s. So you know, this is a real dimension, a real direction. The ring, you could actually see the ring in a microscope and assign a coordinate to what goes around. And so there's the kinetic energy, there's the conservative potential energy, there's the energy that puts things in and out, there's the chi term and the xi term, which don't change anything. So if I sort of put the chi term into the A and just realize that it's built into A, I don't have to put it explicitly, I can reduce this equation to this one, which is the kinetic energy minus the force which can change the energy, minus the conserved force, plus the conserved force, plus the total time derivative of the gauge term. And then on the other side, we have the same thing with different coordinates. We have the flux as a coordinate for a Josephson junction or a capacitor. And we have a force term, which you can write as the flux times the current, Q dot. And then we have a conservative potential energy explicitly as a cosine, which is what's required for Josephson junction. So this cosine is equivalent to this V, which on a circle has to be conservative also, although it doesn't have to necessarily be a cosine. And then they both have the gauge term. And on the left, S is a circle, and C has a continuous slope. On the right, phi has circular symmetry for a discrete spectrum, and C is the same on both sides. Okay, so let's do this here. So let's look at solutions. So I have on the left, there's a ring circumference A, which is a real diameter, and there's a Lagrangian L1D, the kinetic energy, two potential energy terms, and the gauge term, and similar things for a tunnel junction with a current and a generalized ring, where the circumference is not some number, but it's a normal flux quantum. That is a one electron flux quantum, H over E. So superconducting electron is superconducting fluxon is H over 2E. If you have a capacitor which is normal, you can define a flux quantum for that situation, which is H over E. And then so you do the classical solution. I get the classical momentum ms dot, and the equivalent of that momentum is a voltage, C phi dot. Well, C is capacitance, phi dot is a voltage, so C phi dot is a charge. So this over here is momentum, this is charge. They're the same equations, except for the vector potential, which isn't present in the other system. And then we define the operator as we did before, where there's when we go to the quantum version, the canonical momentum becomes a gradient, and there's E0A and d psi ds, and a similar thing on this side. And then the wave function gets the vector potential and the gauge function added in the phase, and the same on this side, except there isn't a vector potential. And both of these equations have the same eigenvalue equation for momentum, which I left as P on both sides. This P is a momentum, this P is a charge. The point is that the operator has a vector potential and the gauge function, and the phase has the vector potential and the gauge function in just such a way that those terms cancel when you apply the operator to the wave function. So you get on both sides, you get that this P op applied to this wave function, this P op applied to this wave function, gives you a gauge invariant. That is, the gauge has dropped out. C has gone away. So is A in terms of this value P. And so P is a gauge invariant momentum. Now, I haven't said what it is. I haven't solved for P. But it's the gauge terms went away. They subtract. There are two of them, one in the phase and one in the operator. And when you put the operator against the wave function, they come out in front and subtract. In just the same way they subtracted in the classical Lagrangian, a couple of slides earlier. So this is a critical slide. So I take the point of view of these Averin, Likarev, and Zorin in the mid-1980s, who took the position that, what I'm saying is what they did implies that the wavelength depends on the choice of gauge, which is what this slide shows. So I just copied the momentum eigenfunction from the previous slide. Here it is. With all the gauge terms, the vector potential, and the C gauge function up there. And then Averin, Likarev, and Zorin applied periodic boundary conditions that there would be an integer number of wavelengths in the circumference because they want a continuous wave function. So there has to be an integral number that means that the wavelength is the circumference divided by some integer z. And if the coordinate advances from 0 to a, the change in phase is given by this equation. So the change in phase is on one side is the momentum, the vector potential multiplied by the circumference, plus delta t. And delta t is the change in this coordinate from when you go once around the circle from 0 to a. And we haven't said whether c has to be continuous. And the argument is that it doesn't have to be continuous because the phase of the wave functions, PS, is not continuous. So if PS is not continuous, there's no reason to make anything continuous. You have to treat C exactly the same way you treat everything else. So PS is not continuous. C doesn't have to be continuous. So in general, it will be some delta E, delta C. So we can rewrite this in terms of the momentum and the wavelength. And we get a momentum times lambda is equal to h, Planck's constant, minus something that depends on c divided by an integer. And you can't get rid of c. You can't just, if there was some reason why it had to be 0, you'd be all set. But I just showed that the momentum itself, the change in the momentum, you go once around the ring, change of momentum is finite. So the change in C, you have to allow that to be finite also. And I call that delta C. And so what this shows is that the wavelength, which is a gauge invariant quantity, for an eigen function, gauge length depends on this arbitrary function, which can be anything. I could multiply this by 1,000. So it makes no sense that the wavelength would depend on some arbitrary choice. And so this shows that for any doubly connected system, and a circle is doubly connected, quantum mechanics doesn't let you let the phase be confined to integers. The phase can be anything. And that's what this equation says. So the Broglie wavelength lambda depends on the gauge choice. Periodic boundary conditions are thus not acceptable for any particle on any circle. And this was left out of physics since 1930. Okay, so we have these two quantum models. So I'm showing this again. So I have a ring where I identified before a problem that we have discontinuous Bloch waves. I'm now saying we have no choice. We have to deal with those discontinuous Bloch waves because the continuous waves are not gauge invariant. On this side, we have continuous waves, and that's just not allowed by the gauge invariant argument. And there's another problem on this side, which is that for a tunnel junction above a critical temperature, there's no periodicity, and there's nothing to give you a charge quantum. And so that's a problem also. And so what I'm suggesting is we can solve the problem of the discontinuous Bloch waves, but I don't know how to solve this problem, that there's no periodic behavior, there's no charging behavior when the junction is normal. And there should be. We should have normal electrons. All right, so what I'm saying is with a ring coordinate account, pardon me? Oh, I heard something. With a ring coordinate, we can account for single electrons and Cooper pairs all at the same time. We can look at the transition. Gee, somebody's did I try that? I don't know. Anyway.
Sorry, I'm late. Sorry.
Okay. So you'll have to, you'll have this whole thing to catch up. We can all look at well, it'll all be saved and we can look at the video. So what this slide is trying to say is, if you have a coordinate with a ring geometry, just the ring imposes periodicity. And then if on top of that there's a conservative potential, like the cosine potential, that also adds periodicity. And if the cosine is a different period than the ring, then you'll get a double situation. That is, we can have two cosines. We can have a cosine, well, cosine like this here, and another cosine here, which represents the potential energy of the Josephson junction. Above TC, when it's a normal capacitor, there isn't necessarily a potential at all, and then you just get H over E. So the length of the coordinate being H over E guarantees that the normal electron, the normal capacitor will have a charge quantum of E. And when the potential grows below TC, eventually the growth of that potential will overwhelm H over E, and all you'll have is a periodicity of H over 2E. So 0 and H over E are the same place in this diagram. It's a ring. Above TC, there's only the H over E period. Below TC, the Josephson potential grows, cutting the period in half to H over 2E. Okay. So now let's consider a Bloch wave in real space. So Luther says that a quantum device that is characterized by a single coordinate will have a single momentum, which I call PK, kinetic momentum. And you can arbitrarily divide this kinetic momentum into a real number Q and another number, which is Z times H over A. So Z is an integer, and H over A is the diameter of the ring, which for a Josephson junction is H over 2E. So I wrote this for a metal ring, like the Broglie experiment in 1983, Broglie paper in 1983. So you can have arbitrary momentum functions which have the same value Q and different values of Z. And you can superimpose those. That is, since they have the same value Q, you can make this superposition here. S stands for superposition. You have QS for the arbitrary momentum. That's the Bloch momentum. You throw in the gauge function here. So when you do the momentum equation or the Schrodinger equation, you account for the gauge correctly. And then you have this sum of a constant BZ and something which only depends on the integer part. So this part is periodic. If it's on a circle, this part will have the periodicity of the circle. This part is not. This part will be discontinuous as Q goes around the circle. So Z is an integer, Q is a specific value, real momentum is a circle circumference, H is Planck's constant, PK is Noether's single conserved momentum, and I will point out that this expression is nice because in the limit as H goes to 0, we're left with the classical momentum, Q. So Bloch waves have a discrete spectrum without continuity and with the classical limit, which the Lagrangian paper and other work like that does not. And so I'm going to get the Hamiltonian. So look what time it is. So I start with a Lagrangian. I have the gauge term in there, and you derive the Hamiltonian as shown here. And PC is dl by ds. So I got this before. And so you can get the classical result right here, which is just repeating what I did before. But I can get the classical Hamiltonian here. This has all the terms. And so you combine all these terms, and this is the classical Hamiltonian. So if we replace PC with the differential operator, this is the quantum operator, with this gauge term in. And like I say, it's an unusual gauge term because the function is only defined on the circle. There's no surface inside. And so it doesn't affect the magnetic field. Okay, so we can write Schrodinger's equation, this h minus h bar d by dt of a wave function that I concocted, so that gamma is just a constant in front and it's an exponential. And if you plug this in here, you get this equation. So there's a part here which looks like parabolic bands. There's a part here where gauge functions cancel, because again, this is strong gauge invariance. The presence of the gauge function and the equations of motion should cancel. If they don't cancel, you're doing something wrong. And then we have two terms that depend on S, Q dot, and A dot. And then we have the energy. And what I argue is that since S is any value of the coordinate, the only way this equation can be true and equal to 0 is if Q minus Q dot plus E0 A dot is equal to 0. And then ET is the rest of it. This adds up to 0. This adds up to 0. And so ET is this this set of parabolic functions. So you can transcribe, I'm talking about two things at the same time. I'm talking about an electron on a ring, which I just did. I'm also talking about a tunnel capacitor, which is the same set of equations. So when it's a normal tunnel capacitor, not superconducting, doesn't have a cosine potential, these equations are exactly the same. And so I draw the band diagram, in this case, of a charged capacitor, where the charge in the capacitor is Q over E0. So it's normalized. And I've normalized the energy so that it's not parabolic, it's straight lines. And so the solid lines here are the exact solution when there's no Josephson potential. And the dotted lines are an approximation, sort of guessing what happens when the Josephson potential is small. And that's the opposite limit of what Google did in last year, because in their case, the Josephson potential got pretty big. They're operating very low temperature. But I'm showing this diagram just below TC. So if you start here at 0 and you put a force on the particle, it goes around, gets to this point, goes over here, goes up here, and then it can change energy. And it goes from this band to this band. Over here, this is the ground state. You can't get lower. But over here, this is above the ground state. The ground state's available. And if there's loss at all, you can get this transition from D to E. And then it goes down here and the whole thing starts over. Each time it goes around, it loses a certain amount of energy. And if you if the cosine potential in, then there are superconducting pairs which don't lose energy. And every now and then, you can go from C to D to F. Now, F and G are special. They're at the same energy. So they cannot exist together. See, D and E can exist at the same time because they have the same Q. That's the Bloch wave. So they can exist at the same time. F and G are different things, but F is close to the -1 line, and G is close to the +1 line, where that's charges. And so if you go from F to G, you're essentially changing number of Cooper pairs. That is, you're changing the number of electrons by 2e by going to F to G, and you don't change the energy. And there's an energy gap. Okay. Now, people in the normal, regular dosage business who pay no attention to the device above TC sort of unfold this and put F and G out here at 1 and -1. And there's nothing going on in the middle. But, there's looking at it this way and trying to understand gauge invariance tells us that we can draw the band diagram close to TC this way, where we don't go from E minus E to E, we go from half a charge minus half a charge to plus half a charge. Okay. So let me see if this will work. See, this is not the normal thing here. Well, so let's see what time it is. So I'm going to skip this. Maybe I can come back.
Sorry about that.
Okay, so what I've done here is I've solved Schrodinger's equation in the absence of a force. In this case, for an ordinary Josephson junction where there's a single period of a cosine potential. And so there's a wave function here. This is the ground state. It starts, it's above 0, goes up, goes down. There's one maximum. And there's the first excited state has 2 maxima. One goes negative, and then the other one goes positive. And these 2 states behave this way in terms of energy. And then you can solve for higher amounts of energy in this situation. And you can see that, especially at lower energy, the bands tend to flatten out, which is something that Google also shows. They get more states inside their picture. So this is what happens when you have a double cosine, that is 2 periods of the cosine going around the ring. And then this one ground state splits. So you get a double period. There's one maximum and another, and this is the first maximum again. And the next state, there's one maximum. So in this case, the lowest energy state I think is the one with one maximum, and then the next one has 2 maxima. But these are very close together. There's a split. So what I'm trying to say is, since I believe everything is consistent when there are 2 periods around the Josephson junction, the bands are split. And this is not recognized at all in the Google work. And I'm not sure what it means, but somehow they should think about that. Okay. So let me talk about entanglement again. So I'm not changing entanglement, but I am changing superposition. So I'm going to do this. Okay. Quantum. The way I would change the definition of quantum superposition, when you see what happens with a ring, not with hydrogen, but which is 3-dimensional and has no holes, but with a ring that's 2-dimensional with a hole for it, the quantum superposition states that some quantum states can be added together, and the results will be another valid quantum state. Conversely, some quantum states can be represented as the sum of 2 distinct states. Since the Schrodinger equation is linear, any linear combination of solutions will also be a solution if the boundary conditions are also linear. So these things are left out. There's an assumption that all boundary conditions are linear, but I've shown that if you assume linear boundary conditions, it violates gauge invariance. So you can't have it. So we get Schrodinger's cat. And so this is an important part, I think. And so I'm not killing cats. I'm feeding them, or a cat says, I wish I was an electron so I can be in 2 places at the same time. Cat would like to sleep and eat simultaneously. It's ordinarily not something possible to do. So if there are quantum states related to sleeping and another quantum state related to eating, you can imagine that if you were a cat, you might like to superimpose them. And what I've shown is that for these ring junctions, there are many states that you're not allowed to superimpose. So it's quite conceivable that the cat could have states that you can't superimpose. So if these states for eating and sleeping have some circular symmetry with a hole in them somewhere, it's quite conceivable. When the mitochondria inside the cat have this property, it's conceivable that you're not allowed to superimpose death and life, or sleeping and eating, or other things that you might like to superimpose. You can't just assume that things are superimposable because it's quantum. You have to show that they're linear boundary conditions. And for the ring, they're not linear. So that's the dilemma of the cat. A simple rotator has some unsuperposable eigenstates. Maybe that the quantum limit, eating and sleeping, are also unsuperposable eigenstate. And the cat problem is solved, at least for some quantum activities of cats. So some unconventional consequences. The boundary conditions for a Schrodinger wave are non-linear. Okay, that's different from almost everything. The boundary condition for the hydrogen atom is perfectly linear. It's because it's three-dimensional. And any path you take through three-dimensional space has to go between 2 points by lots of different paths. You have to get exactly the same difference. Whereas in 2 dimensions with a hole, that's no longer the case. You can have, it goes around, the endpoints can be different. And so it's a nonlinear situation. There's a continuous spectrum of non-superposable eigenfunctions on any circle. A subset of eigenfunctions are superposable if they differ by h. All Schrodinger waves on the circle are Bloch waves. The Coulomb blockade, it's a gap between bands, should be observable in a single isolated tunnel junction. You don't need a more complicated circuit. Above TC, a single electron determines the ring circumference, h over e. And below TC, the Cooper pair pairing determines the potential period h over 2e. So as you go through the transition from above TC to below TC on a Josephson junction, you're changing from a single electron to Cooper pair tunneling. And if the Josephson potential gets big enough, that eventually dominates. There's a whole bunch of things which are worth thinking about. So for this system, Noether says, Noether says that there's a single conserved momentum. The boundary conditions on a circle are nonlinear. A circle has an infinite quantity of momentum eigenfunctions. An applied torque can continuously change the energy of the rotor. That's something that was demonstrated, the quantum thing that can work. Compact space implies discrete eigenfunctions or Bloch waves. Discontinuous Bloch waves can be defined on a circle. The Bloch momentum becomes classical in the limit at h goes to 0, which is not true of the equation set up by Lagrangians et al. Separation of variables. There is a separation of variables in Schrodinger's equation, which allows a good solution. A subset of momentum eigenfunctions are superposable. For a junction above TC, the circumference quantizes the charge E. Below TC, the Josephson potential quantizes the charge 2E. So here I show a picture from Google's paper, or at least a version of the paper that I found. And so they show something 300 microns long, and the Josephson junction is way in here. And the actual junctions are quite small. They have 2 of them, so they can tune the critical current of the combination with the magnetic field. And so there's a diagram of this down here. And what they're saying is there's a single cosine potential, which in this case has 4 quantum levels. And so what I'm saying, if I'm right, then there's actually 2 periods of the cosine potential, and all these levels are split. And the ones higher up get split more. And it's possible that they have to be careful about this as they go about measuring system. And they should at least acknowledge that that's what could happen. They don't talk about the coordinate. You know, they're not sure what to say. I never saw a clear statement of whether it goes to infinity or it's a circle. And so my theory is it has to be a circle. If it goes to infinity, it gives the wrong answers above TC. Okay, so I worked out some parameters for this Google paper, and one of them is that there's a plasma frequency of 6 gigahertz, 2 pi there, and so these are these Josephson equations. There's this plasma frequency squared, and from that information and looking at some of their figures, you can calculate what their critical current might be and what their capacitance might be. So I think these are fairly reasonable values. But I you know, for the critical current, this is I think a very decent estimate. They didn't say what their critical current was. They also didn't say what their capacitance was, and so I'm coming up with this estimate for people to do circuit models. And that's the end of what I had to say, aside from trying to show these diagrams. Okay, thank you.
Well, it's hard to clap silently. Sorry about that. Thank you.
So I have 3 minutes to ask questions.
I'll open up the floor.
Let's see if I can. Let's see.
And in case we can't see your hand raised, if anyone has questions, go ahead and unmute and speak up. Sorry, we had some Zoom bombers earlier, like actual real Zoom bombers.
Let's see, can I change this pointer? Let's see.
Yeah, if you maybe change it in the pointer options back to the mouse, maybe that video will work.
So let's see, pointer options. What do I want?
And another way maybe is to stop full screen.
Let's see. Okay. So this is my simulation. I have 4 views of the wave function and the potential. So let me stop this. So
do you have so we can't
it's the real, excuse me?
We can't see the video.
You can't.
I think you might have your screen selected as the PowerPoint, but sometimes you need the whole, like your monitor when you share your screen, and so it might just be if this popped up, we can't see it.
Yeah, so Zoom only allows sharing one window at a time. You can stop sharing and share again, and share the video.
Let's see. How do I get sharing back? Let's see.
Yeah, the first thing would be to ESC and exit the
stop share, and then I can do share screen. And
then if it asks you like to select one, you can just select the whole.
So do you see it now?
Yes.
Okay. Let's see if I can get it working. It's stationary.
Oh, okay.
So you know it's let's see. It won't show the arrow. Well, you know, I'll be sure to include the file that shows this. And what I'm calculating in this top left square, it's the real and imaginary part of the wave function. So it starts out as a point and it goes around in a circle. In this rectangle to the right of that, it's the magnitude of the wave function. This wave function squared. So the particle is in the whole 2 pi phase space and has an absolute value of 0.4. Down below that, I show the parabola going from minus 0.5 to plus 0.5. Well, it goes from -1 to 1, but the solution goes from minus 0.5 to 0.5. And then in the sort of 3D thing to the left of that, that shows the whole wave function. The bottom plane is the real and imaginary part of the wave function. And the coordinate going vertically is the phase of the wave function. And so it shows that it's discontinuous, and you can solve it despite being discontinuous. And you know the solutions this give dynamically look exactly like the parabolic diagram of the energy of the wave function. So I'll stop sharing, I guess. So let's see, the chat has one thing on there.
Oh yeah, Roger said he had to duck out.
Okay.
4:50.
You know, I'm not an expert on quantum computing and qubits, but you know, my reading of the Google paper, and you know, I watched Aronson's talk that he gave a couple of weeks ago, and he didn't give numbers for the dosage junctions either, so, and they weren't in the paper except by inference. But you know, I think Google did a pretty decent job. And if they're way below TC, they may have two periods of the cosine which don't talk to each other because their energy is too high. So it could be that just doing one of those is okay. But you know, it may be an important detail that they may have actually two periods and then split levels of their energy levels. And like I say, as far as I can tell, I'm the first guy to worry about the gauge invariance problem of a particle in a ring.
Yeah, very nice. So if we have no questions, maybe we can thank Arthur again.
Yeah, thank you, Arthur, for
You're
coming.
You're welcome. It's my pleasure. It's been a while since I've given a talk.
I can stop recording.